Hey there, how are you? My name is Mohamed Samir. I'm one of the founders of Computer Dove. Thanks for tuning in. Today we're going to be studying the seventh lesson in the SAT physics program, energy, work, and power. First, we have to understand that the meaning of energy is difficult to define. It's not very straightforward as most of us would like it to seem. So as we're working, I'd like you to focus on the specific rules, the specific meanings, and try to understand and have an intuition of what's actually being required for you to understand. Okay, first things first is kinetic energy. Now, kinetic energy is expressed by K, and it is equal to half mv squared, as we may see, where m denotes mass and v denotes velocity. Now, the kinetic energy is directly proportional to mass and and directly proportional to v squared, and it's a scalar quantity. Now, potential energy potential energy is the energy possessed by an object based on its position. And so what does that mean? That means when you have an object and you start lifting that object, you start getting a pen and you get it upstairs or something, you're actually putting energy into that object. If you have a roller coaster that's starting to climb, you use energy even when it stops. So you have this car and you start lifting it into the air, and then you stop lifting it. Now it's suspended in the air. It doesn't have any kinetic energy, so it stops. There is potential energy in it, because potential energy is possessed when an object has a new position. That is height above the ground. So if I bring my phone and I raise it, then my phone has potential energy. What is potential energy? Potential energy means energy that is capable of producing kinetic energy. What happens if I let my phone go after I raise it? Well, the phone will have kinetic energy. So that's the meaning of potential energy, and it's very important. And so the example I was talking about, is just gravitational. There are many things, like if you have a spring and you are, putting it, or I shall say, compressing the spring. What happens if you let go? Well, a lot of kinetic energy is going to happen after that. So that is called putting potential energy into a spring. But there is also gravitational potential energy. And so here, as it's saying, gravitational potential energy is due to the position of an object in a gravity field. So a mass in Earth's gravity field is pulled towards the Earth by gravity. And when the mass is raised to a height of h, that mass, in proportion, will accelerate towards the Earth if it is released. And at height of h, the mass has a potential to create kinetic energy. That is why it's called potential energy. So how do we calculate this potential energy? Potential energy is called is denoted by U of G. It's mgh. So it's mass times acceleration due to gravity, g, times h. And since this is SAT physics, the g is going to be 10 meters a second squared. While the acceleration due to gravity, the real acceleration due to gravity is 9.8 meters a second, but it's approximated because you're not allowed to use a calculator on the test. Okay? So as of kinetic energy, potential energy is a scalar quantity. So it doesn't matter where you put your directions when you put velocity. So we've talked about gravitational potential energy, kinetic energy. We need to talk about elastic potential energy. Elastic potential energy is the potential energy associated with elastic devices. springs. And so, how are you going to calculate um, the potential energy of a spring? Well, we have to know Hooke's law. Now, Hooke's law says this is Hooke's law right over here, and it says K multiplied by X. Just in case you're unfamiliar with this, K is Hooke's constant. It's the spring constant, excuse me, and X is the displacement of the spring. So it's also called delta X. In some physics books, it's going to be delta X. Now, what does this mean? When you have a spring and you move it down, or you move it to the right or left, you're moving it by a distance, delta X. Now, this delta X, okay, multiplied by a specific number that is specific to each spring. Okay, so the problems you will take will say K is equal to, or the spring constant, because that's is K, is equal to something. You will take it and you will multiply that by the displacement times X, and you will have F of S. What is F of S? That is the force the spring exerts. Now, why is the force exerting? Why is the spring exerting a force? Well, you're actually, it has a natural position, and what you're trying to do is change its natural position. It will try to restore. It will try to restore the spring back to its original position. So that is why you're going to have a restoring force, and you know how to calculate it: K multiplied by X. Okay, so let's continue here. Oh, forgot to erase that. So when a spring is displaced a distance of x and is subsequently released, the restoring force accelerates the spring back to its original length, right? I'm moving the spring. Spring wants to the spring wants to return back to its original position. So when I release my weight, or when I release my hand, the spring will return back to its original position. So how did it do that? Like it had kinetic energy. Well, there must have been a potential energy to make it move in this fashion. So what is that going to be? That is going to be half k of x squared. That is the potential energy. Displacing the spring has the potential to create kinetic energy, and that is how you are going to calculate. Now, half k is the spring constant, and x is the displacement of the spring, and you do that squared. We're going to understand how this was done exactly. Why? Just in case you want to know how it was derived. So it's important that we put some notes here. Elastic potential energy is directly proportional to the spring constant K and to the square of the displacement x squared. Okay. Now we come on to a very, very important conclusion here. Now we know we have taken the potential energy and the kinetic energy, and we understood that potential energy can either be elastic or gravitational. Now we move on to total mechanical energy. This is always in this fashion, not mechanical. You have to say it. Total mechanical energy. Total mechanical energy is the sum of the kinetic and potential energies in a system. So total mechanical energy is an instantaneous value. So here's what it says. Here's what it says. When you have a ball, let's draw this. So this is the ground, and this is a ball, and the ball is going to drop and hit the ground. So I'm actually holding it with my hand over here. So I'm going to release that ball. That ball is going to fall, right? Well, that is correct. So it has potential energy at the moment. That is going to be mgh. That is how you do the potential energy, right? And so as I release the ball, what's going to happen to the speed? It's going to increase. So the ball will actually pick up some speed until it hits the ground, and it's going to hit the ground with kinetic energy. So the kinetic energy as we're falling will increase. The ball will get faster and faster, kinetic energy increases. There's also something that you must know. The potential energy of the ball as it is falling is actually decreasing. Why is that? Because the total mechanical energy equals K kinetic plus U potential. The total mechanical energy is constant in the whole operation. The ball, as it was falling, the uh, total mechanical energy has to be constant because energy cannot disappear, right? It cannot disappear. And so, as I was dropping the ball, okay, let's use another color here. As I was dropping the ball, the potential energy got less and less, and because the total mechanical energy has to be constant, we have kinetic energy compensating, and the kinetic energy is increasing more and more and more. And so when we hit the ground, okay, we will have kinetic energy. It was increasing, increasing. When we hit the ground, the kinetic energy will be maximum value, and the potential energy will reach zero. Well, why did it reach zero? Because it was decreasing and decreasing until it reaches zero. All right? Well, let's assume another example. Okay? Let's assume I'm going to throw a ball upwards. Okay? So I'm throwing it with kinetic energy. When it reaches the top, it's like gonna climb and it's gonna free fall back again. So it's gonna climb. What's happening to the speed? Speed is decreasing. And because kinetic energy is decreasing, the potential energy has to increase. So the potential energy increases, increases, increases. Until it reaches the top, the kinetic energy will reach zero, and the potential energy will reach its maximum value. And then when it falls, conversion starts to happen. The kinetic energy increases again, and the potential energy starts to decrease. And so that is why total mechanical energy is so important. It's the sum. And total mechanical energy is constant everywhere in the problem. The total mechanical energy, which is this guy right over here, is constant everywhere. So here we have an example. A pendulum is initially at rest at point A, and it's released and swings through points B and C. What types of mechanical energy are present at point A, B, and C? So we're supposed to know the formulas that we're going to calculate the total mechanical energy at each point. All right. So in this point right over here, in this point A, is there any kinetic energy? No, it's actually stopped, and it's going to increase its speed, reach here, and has maximum speed. So here, kinetic energy equals zero. Kinetic energy equals zero. Potential energy is maximum. Correct? Correct. Well, how do we calculate kinetic energy? mgh, mass times acceleration due to gravity times height. So we will write, just going to choose color, mgh. Point B. Now at point B, what's happening to the potential energy? We don't know. Okay, what's happening to the kinetic energy as the ball is going to point B? It's increasing, right? Kinetic energy is increasing, the speed is increasing. Both are the same, essentially. Now, because the potential energy is increasing, the kinetic energy has, because the potential energy is decreasing, the kinetic energy has to increase. So let me say that again. Because the kinetic energy is increasing, the potential energy is decreasing, right? So we have, in this instance, we still have kinetic, we still have potential energy, and we still have kinetic energy. Well, we have potential energy mvh, and we have kinetic energy half mv squared. And then we've reached point C. And in point C, we don't have any potential energy whatsoever. It's all been converted to kinetic energy. So we will say point C, we have half mv squared. Okay. So now we're going to go to the trick. Well, these are the answers. Of course, I'm right. Okay. Now we have another example. A ball has mass and speed and therefore has kinetic energy. What is the effect of the kinetic energy of the ball when the speed is doubled? When the speed is doubled, we're going to go, this is the formula, k equals half mv squared. So instead of v, we're going to put 2v, half m, and we're going to remove the v and put in that bracket 2b. So what will happen is, not very clear right over here, we'll have half m 4v squared. And so here we have a secret 1, but now we have 4. Okay, so that means the kinetic energy was multiplied by 4, and that way we will understand that the speed was quadrupled. Okay, now we move on to work. Work is a very important phenomenon to understand in the SET physics and in physics in general. So work is the process of applying force through a distance. And so to understand work is basically force times displacement. It's always like that. It's force times displacement. And so what we have here is work equal force average times the displacement parallel. Now, what does this mean? First, what is being assumed in this case is that the force is not constant. Well, when we were working with work in previous problems, we were assuming that the force was constant, like a force of 20 newtons is work. But what we will see in this example right over here is the work has a force that is increasing. And so what do I do if I have actually a force that is increasing or decreasing? I'm going to take the average of that force. That is why we're going to use average of that force. Okay, so we have F AVG multiplied by the displacement parallel. What does that mean? That means we're going to multiply the average force by the distance that is parallel to that force. So if I have a car, okay, it's a very weird car, but let's just say a tire, and there's being work exerted on that tire, and the tire moves in that direction. I'm going to multiply that work with that distance right over here. Because the work is moving in that direction, displacement is moving in that direction, and therefore we can use this displacement as well. But what the problem happens is, here's what the problem is, okay? And this is little part of my experience with problems, is we say, for example, that you're traveling, congratulations. So you're on vacation. I don't know how you're going to do that in the midst of the coronavirus situation. And so you have this bag, and you are pushing it with a force in this direction. And let's say that force is 30 newtons, okay? And you moved 50 meters. A big problem people would say is that's easy, 30 times 15. That is wrong, because the distance is not parallel with the force. So how do you bring the distance that is parallel with the force? Well, an easy way would be to break down that force component into that force resultant into its components. So you'd be given that, for example, there is 30 degrees here. So you'd say, alrighty, that is going to be, we're going to just complete the triangle. So the side opposite 30 is half the hypotenuse. I'm sorry, this is a very bad triangle. So that is going to be 15. That's a special triangle. That is going to be 15 root 3 newtons. So what you're going to do in this case is multiply 15 root 3. The work will be force on the x-axis, 15 root 3, multiplied by displacement. That is the work that has been done. Okay? So let's just remove these drawings. Okay. We have the example, the same thing I was talking about. I promise you, I did not know it was coming very much. So we have the figure above. Mass M is pulled horizontally to the right by force of F, inclined at angle theta, and force F and its components are shown in the diagram. The surface is rough, so we have friction small f opposing the motion. Determine the work done by the applied force F. So try to pause the video for a moment and try to figure it out for yourself. If you can do it, let's do it together. So what we have said is F cosine of theta, because that's the way to bring the component on the x-axis, which is F cosine theta. So this is the one right over here. So F cosine theta multiplied by the displacement that we have actually. Okay, so that way we know the work by the applied force. But then we need the work done by the friction. Here we have a problem because the friction is doing force that is in the opposite. It's in the opposite direction of motion. It's in this way. So we're going to put a negative sign. So we have negative F multiplied by delta D. Actually, if we really need to know where this negative sign came from, we need to do something very simple. Okay, and so this is not very like necessary to understand, because in the SAT physics you're not actually required to understand how things come to be. You know, you just know the rules, but it's better to have a basic understanding of where we get the rules we have. Now what we understand is we have to get the x component and multiplied by the distance. So that is F cosine theta multiplied by the distance. So we're going to say this is the distance going, right? Right. Where's the force? Okay? And so the angle between the distance and the force is 180. And so you're going to say F cosine of 180 is -1. So that is how you get this right over here, that negative. So you can use either rule, but you have to bring the theta between, or the angle between the force and the displacement, and put it in this rule right away. It will never let you down. Okay, let's do that. Okay. So now we're going to go into the work of gravity. So we understand that potential energy is equal, I'm sorry for that sound. Potential energy is equal to mgh. Well, work is equal to force times displacement. And so if you drop an object and you want to see the work done by gravity, that is the same thing as saying mgh. And so work done by gravity is equal to the potential energy of the object. But to put it in a clearer sense, we're going to see it in first. So here we have a pretty nice problem. Okay, let's do this. In the figure above, mass M is positioned at the top of a frictionless surface with an angle theta. So we have theta right over here. The mass slides down the incline at distance d. Determine the work done by gravity. Well, So there are two displacements occurring as this object is falling. You can use either one. Okay, so this is what I mean. Work is equal to F average multiplied by the displacement parallel. So you can either use this or that. Here's what I mean. We need to find the work done by gravity. That's what's required. So the work done by gravity, well, gravity is working in that direction, isn't it? So you're going to use the force due to gravity. The force due to gravity is mg. It's the mass times acceleration due to gravity, right? That's the force of gravity, okay? So it's going to be mg, force due to gravity, multiplied by the height or the parallel displacement. What's the parallel displacement? That is delta H. That is this place right over here. So the force, Fg, times the height. We know the force due to gravity is mass times acceleration, so it's mg multiplied by h. Hopefully that makes sense. Okay. The other thing that was not mentioned here was you could actually use this delta D right over here, but you need to bring a force. And you probably understand inclines by now. And so what you can do here instead, say, well, we understand that the force due to gravity that is parallel to the incline is equaling mg sine theta. So we can say mg sine theta multiplied by the displacement. But the most important rule is they have to be parallel. So this is parallel with that, so it's a good problem. But if they're not parallel, you can't say mg multiplied by delta d. That's wrong. Okay? Well, hopefully you understand this. Okay. Oh, I forgot to clear. Okay, so now we move on to a very important lesson. And this was one of the lessons that I had a very hard time understanding. So this is work of a spring. So try to focus here what I'm saying mostly, other than what the book is saying. The work of a spring is done when a spring is stretched or compressed. So the spring is doing a force that it counteracts your motion. So since it's doing a force, there has to be work, right? Well, that is right. The work of a spring is a good example of the work done by a variable force. What is variable force? Variable force is force that is changing, force that has acceleration that is acting on it. So the force is changing. So that is why when we do work with a variable force, we bring the average force instead. So spring obey Hooke's law, which the spring force is kx. The restoring force F of s is the instantaneous force in a spring. So let's look at this graph. This graph is gold. Okay, it is telling us how the spring is reacting. This is on the y-axis. We have the force done by the spring to bring the object back to its original position, and here we have x. And if you bring the slope, okay, you will get let's do this. Okay, what is slope? Slope is y over x, so that is f of s divided by x. Same thing as saying k. Okay. No, excuse me. That is terribly wrong. F of s divided by x. Well, that isn't going to equal something. Sorry, I got confused. You can ignore that. So what you're going to see here is FAVG, the average force. Well, what is average force? It's going to be half F of S, half the force Average force is half the variable force. Now, why is there a variable force? Well, the spring is actually trying. You have the spring right over here, so and you're pulling it. You put 20 newtons, so your pull and your force is constant, right? And what's happening? The force, the spring is trying to exert force, but still 20 newtons is 20 newtons, right? And so it still comes down, and then it's trying to increase, trying to catch up until it finally catches up and it stops getting down. All right? And so it's doing the force. And so to find the average force, you just have the total force, the final resultant force. That is the FAVG. So the point of this point in the lesson is to show you how we bring the potential energy of the spring. It's pretty important, right? Okay. So the work formula uses the force acting when the distance is changing. So we have this is normal. FAVG is equal to half kx. Okay. Hopefully this makes sense. Okay. Now here's why. Here's why this should make sense. You understand the average force is equal to half the final force. Now what is the final force equaling? It's Hooke's law, kx is here. So FAVG equal half k of delta x. So when we bring the potential energy is equal to the work equal force times displacement. Let's say this, work equals change in potential energy. This is very important for us to understand. This is a new point. But work always is equal to the change in energy. It's equal to the change in potential energy, and it's equal to the change in kinetic energy. So what is work? Work is force times displacement. We know what the force is, right? The force is half k delta x. That is going to be half k delta x. That's the force. What's the displacement? Delta x. So when you multiply that, you get half k delta x squared. That is equal to work. It's equal to the change in potential energy of the spring. Okay? Write this down. This is very important. And so we have the work that is done is half kx squared. It's also called the potential energy done in a spring. Now we move on to the work of the spring. We have a problem that we're going to solve. A 4 kilogram mass is attached to a spring with a spring constant of 20 newtons per meter. The mass is lowered 0.50 meters to equilibrium, where it remains at rest. How much work was done stretching the spring? Well, that is going to be half k, which is the spring constant, 20 newtons per meter, and it was lowered 0.5 meters. So that is 0.5. That is a bit 5. Power 2. And so that is going to be half. That is going to be, yeah, that's going to be 2.5 joules. So we understand that the mass attached, oh, yeah, the spring was not stretched initially. Okay. So whatever, you get the point. Oh. So this is what I was talking about. Remember when I said that work equals change in potential energy? Well, work is always equal to change in energy. So the work kinetic energy theorem states that work is equal to the change in kinetic energy. When one or more unbalanced forces act on a mass, that mass will accelerate, changing in both speed and kinetic energy. So the net work equal change in kinetic energy. That's a very important rule right over here. Try to memorize it. Let's look at this problem. Changes in speed and net work. Okay. A 2.0 kilogram mass is moving at 4 meters per second, is acted upon by a force which does 20 joules of work on the mass. Determine the final speed. Well, the net work in this problem is 20 joules. So as it is said, 20 joules is equal to half the change in kinetic energy. So we'll bring half, we'll change in kinetic energy. Well, the final, we don't know the final kinetic energy, okay? We're required to find the final speed, so we don't know what the kinetic energy is, because kinetic energy, half mv squared. And so if you don't know the speed, you don't know the kinetic energy. So you have half mv squared minus what you know, and doing your manipulation, you will get that the final velocity is 6.0 meters a second. Okay. Now what this section already says is when we have an object that is rotating in a circle, there isn't actually any work that is acting because there's no force, there's no change in kinetic energy, you know, no change in kinetic energy. The velocity is constant. There's no acceleration action. This is a very important part for SAT physics. It's the area under the curve. Okay? The area under the curve, FD, when you multiply F by D, you get work. Well, in this graph, when you multiply the x-axis by the y-axis, you get this area, which will equal the work. Okay, so if you're given here, for example, 10 newtons, and here you're given 3 meters, you need to find the work. Multiplying by 10 by 3 will give you the total work that has been done. You just bring the area, okay? And so the area was F times D. If you have a triangle, that's no problem as well. Like here we have this problem, and I'm required to find the work. So I will say, oh, that is easy. What's the area of this triangle? I'm not going to bring this distance right over here. Okay, so it's going to be half base times height. Hope you forget what the area of, hope you remember what the area of a triangle is. Half times 8 times 4. It's going to be 16 joules. Am I right? Of course not. Okay, now we are talking about power. Power is it's kind of a wonderful concept. It is work divided by time, and it's measured in watts. So we understand that work is force times displacement. I love my pen. It's force times displacement. I'm going to divide that by time. And so what you can realize here is that displacement divided by time is velocity. So instead, if you're given velocity, you can say, oh, that's easy. That is force times velocity directly. Okay, let's do a couple of problems here. Determine the power required to lift a 10 Newton crate up to a 400 centimeter high shelf in 2 seconds. What you can do directly is, what's the speed? The speed is meters a second. We get 4 meters in 2 seconds. Speed is 2 meters per second. Multiply that by the force. So you're going to say, well, you got you got work, you got power equals force times velocity. So that is 10 multiplied by 2, you got 20 flies. Okay, determine the power required to lift a 10 Newton crate vertically at a constant speed of 2 meters per second. This one's easy. Just multiply the force by the velocity immediately right away. Now we're going to go into a very important lesson, conservation of energy. Um, Now we understand that total mechanical energy is always constant. You know, potential energy plus kinetic energy always has to be the same value. So this is a very important rule that you have to take. Ki plus ui equal kf plus uf. Since total mechanical energy equals ki plus ui, the sorry, since the total mechanical energy is equal to Ki plus Ui, and since they are both equal, then Ki plus Ui is equal to Kf plus Uf. Please understand that the U denotes potential energy. Let's work off this problem right over here. The conservation of energy. So a boy standing on a ledge throws a ball with a mass of 0.5 kilograms straight up into the air with an initial velocity of 20 meters per second. The ball is initially 5 meters above the ground. It rises to a maximum height and then falls, missing the ledge on the way down. So it's going to fall on the ground. The ball impacts the ground 5 meters below its initial starting point. What's the total mechanical energy of the ball as measured from the ground? Total mechanical energy is the same, so you can measure it at any point. Okay? And so you can say total mechanical energy is equal to half mv squared. And so say half m, well, the ball is half kilograms. V squared is velocity. And so you will also notice that the ball is at a height of 5 meters. So you will add to that kinetic energy, potential energy, which is 0.5 times 10 times 5 mgh. You're going to get 125 joules, and 125 joules is called total mechanical energy. It will be constant every single point. What is the total mechanical energy of the ball 2.0 meters above its release point? Well, it's going to be the same. Total mechanical energy is similar everywhere. What is the maximum height reached by the ball as measured from the ground? Well, we're going to use only in this, I'm going to only explain the energy solution, okay? Well, we know that Ki plus Ui equals Kf plus Uf. So half mvi squared plus mgh equals half mvf squared plus mgh. So you've essentially got the initial kinetic energy plus the initial potential energy equals the final kinetic energy plus the final potential energy. So the left side of the equation was calculated in part A. So you got 100, you do your manipulation, you're going to find the final height in the end. Okay. So a 0.02 kilogram pendulum bob is released from position A, and as the pendulum passes position C, located 1.25 meters below position A. So let's draw the givens. Where's my pen? So here the distance, 1.25 meters. Oh, that is a very British accent. I apologize. Below position A. What is the velocity? Okay. We need to find the velocity at point A. So I'm going to solve this problem with you, and I'm not going to look at the answer. All right? All right. So I will say Ki plus Ui, initial kinetic energy plus initial potential energy equals final kinetic energy plus final potential energy. Well, the kinetic energy at the top, at point A is 0. Okay, and and the potential energy, well, that is mgh. Well, I know the ball is 0.02. Okay, this is starting to look like a challenge for me. M times g, acceleration in gravity, times h, which is 1.25. Okay, I always do the big number 5 over here. That is going to equal the final kinetic energy. What's the final kinetic energy? Well, I don't know. That is half. The mass doesn't change. Mv squared plus 0. Well, the potential energy at the bottom has disappeared. So this is what we're going to have. And true enough, that's what they actually do. And using manipulation, using mathematics, stuff that's out of my realm and out of my time here, you can bring the final velocity. Okay. Oh, let's just really erase that. Okay. Now we have a very important test problem that I have seen come on my test. Okay, where's my pen? Okay, without a pen. A 1.0 kilogram block moves with a speed of 10 meters per second and strikes a spring. Okay, so it's moving, it's hitting the spring that has a spring constant of 25 newtons per meter. Determine the maximum compression of the spring. Well, finally my pen is coming for my survival. Well, in order to solve this problem, okay, we have to assume that this object has already hit the spring. And so remember when we said that potential energy is not only gravitational, but there's also an elastic potential energy, and that is equal to half kx squared, right? So using the same rule, just to give you a sense of how important this rule is, ki plus ui is equal to kf plus ul. I'm just going to give you a hint of what each letter is going to be. Ki, initial kinetic energy, is equal to the kinetic energy of the box. That is half mv squared. Mass is 1.0. The v is 10 meters a second. Okay, and so half mv squared is going to be your total initial kinetic energy right over here. What am I doing? I'm just pointing at it. Okay, the U, which is the potential energy, well, potential energy is 0. Now, I'm not referring to the potential energy of the cube or of the object. I'm referring to the elastic potential energy of the spring in this problem. Okay? So, we will equal that to the final kinetic energy of the spring, which it's going to reach a maximum compression. The spring is not moving, so the final kinetic energy will be 0. And its u of f is going to be its potential energy. How am I going to calculate that? It's going to be half kx squared. Well, I know the k, and I don't know how it's going to extend. So I'm not just going to write that and waste my precious ink. Okay, we have it right over here. So we have half mvi squared plus the kinetic energy of the spring, which excuse me, plus the initial potential energy of the spring, which is 0, equals the final kinetic energy of the spring, 0. Okay, and it's compressed, so it has final potential energy of half kx squared, half 25 times x of x squared. We have very much reached near the end. I don't know if we have done so or not. Let's move along. Okay. So a 50 kilogram skier, I think that was me 1 point ago, but no longer 50 kilograms, is skiing down a 5-meter tall hill, inclined at 30 degrees. The skier arrives at the bottom with 2,000 joules of kinetic energy. How much energy was lost due to friction? Well, that is an easy problem. Energy is never lost. Ki plus ui equals kf plus uf. Energy is never lost. Just doesn't happen. And so, what's the energy going in? What's the energy going out? So we will say, here's a different formula. What's the energy up here? Has to be the same here. Here, you will have potential energy. Okay? It always comes to the same rule. Upstairs, you're not having any kinetic energy. And downstairs, you're not having any potential energy. So the potential energy upstairs equals the kinetic energy downstairs completely. Has to be. So what's the kinetic energy upstairs? That's mgh. That's potential energy. That's m times g times h. Well, the mass is 50. Axial due to gravity is 10. Height is 5. Let me save you the effort. That's going to be 2,500 joules. I'm so sorry for my handwriting. This gear arrives at the bottom with 2,000 joules of kinetic energy. Wait, 2,000? What happened to the 500? How much energy was lost due to friction? You're a smart person. Subtract 2,500 from the 2,000. 500 joules was lost due to friction. And this makes complete sense. Energy can never be lost. It's converted into friction, into heat, into sound, whatever. Okay? And by that, we have reached the conclusion of our lesson. Please study well. And if you have any kind of problem, please ask them to me personally or in the comment section below. Thank you very much, and see you later. Oh, and by the way, for all these virus channels trying to make comments, please stop doing so. I just erase your videos. They just give me awful good of entertainment. Oh, bye bye.